Hi. Since taking over Baldy Cat's channel and turning that into Mr. Sensible, I had decided to mirror a few of my original videos. This one is one I'm particularly proud of. It was my MAGE experiment when I sent a balloon to the very edge of space. The MAGE experiment caused rather a lot of consternation amongst the flat earthers. Several tried to debunk it. They all failed. I hope you enjoy. Take care.
With logic and cheese.
Hello, I'm Mr. Sensible. Welcome to MAGE 2, Mission Above Globe Earth. How many times have you heard flat earthers claim that the Earth is not a sphere, that there is no evidence for it being a globe? Well, whenever we see high altitude footage of the Earth, it looks like this, all bending and flexing because of wide angle camera lenses. I had an idea, and when I put it out, I had great support from super chats, from members, from patrons, and from 3 wonderful sponsors. Mr. Sensible is proud that MAGE, the Mission Above Globe Earth, has been sponsored by Bob the Science Guy and his channel, Common Sense Science. I'm also proud that MAGE is sponsored by Arctic Haze and his Climate Anomaly website. MAGE is now also kindly sponsored by Just Shoot Me, a Canberra-based rigging service for para and hang gliders, sailplane pilots and skydivers. I appreciate and would like to thank each and every one of my wonderful patrons. Thank you. Additionally, I'd like to give a very special big thank you to Q, an anonymous guy who has donated very kindly of his time and his experience. He's loaned me equipment. Without Q, without doubt, this whole experiment would not be the great success it is. So massive thank you, Q. So what is this big problem with the videos taken from high altitude balloons? Almost without fail, they're using wide angle cameras, action cameras, GoPros and the like. Now those cameras are great. They give you a great field of view, but they suffer from distortion, barrel distortion. Now if what you're filming is pretty much across the centre of the field of view, your distortion with these cameras is virtually non-existent. But the further you get above or below the centre of the field of view, the greater and greater the distortion becomes. If you're above, then it bulges upwards in the centre. If you're below, it bulges downwards. Now if you're trying to measure a curve of the Earth, this isn't very helpful. So I thought, why not use a narrow angle lens, a non-distorting lens? I say non-distorting, but all lenses will distort to a certain amount, but let's keep it to a minimum. Additionally, I thought, why not have a reference frame that's kept in view the whole time, so that there can be no accusations of digital manipulation. So my idea was to have a taut string right across the centre of the field of view. This was improved when Q suggested having 2 strings. Now these strings are spring loaded, so at all times they're straight. They're held away from the probe using a balsa wood framework. This was MAGE. Now when I announced all this, it was met with some real enthusiasm. People really seemed to like the idea. One guy, Andreas Puelma, who's an engineer from Chile, even did some calculations and came up with this. This diagram shows the expected amount of Earth curvature at a height of 39 kilometres, which was the target height for MAGE. Now it'll be interesting to green screen that over the video to see if we get anywhere near a fit. So thank you for that, Andreas. That's also much appreciated. So I think we better get started then. Go MAGE! Here we go, ready for MAGE 2. As you can see, the weather looks a bit better. We got high cloud deck. It's broken in a few places. Hopefully we're going to get a good view and some good height. And here we are, MAGE 2, sponsored by Bob the Science Guy, Arctic Haze and just shoot me. We now have the sensor for air pressure and temperature sheltered under here, so it's not affected by the heat from the sun. And MAGE is rebuilt. You can see the two taut reference frame lines. So, inside MAGE, first of all, cat biscuits for Arnold. I've upgraded from cheese triangle to a Babybel cheddar cheese. And of course, the MAGE mission patch for a lucky winner. So fingers crossed, MAGE 2 today is going to fly. We waited until the wind had dropped before filling the weather balloon. Of course, just when we were ready to launch, the wind picked up again. Now, although the balloon of course will still go up even with this wind, the problem is it will go sideways quite quickly, which means that the payload, MAGE, will get dragged across the field, banged and bashed about before it finally lifts off the ground. That's not a good idea. So it's a case of waiting and waiting. And of course, the more we waited, the stronger the wind seemed to get. We reached the point we actually considered abandoning. But patience won out in the end. And very shortly, the wind dropped again. Taking advantage of a brief lull, the idea is to run forward with the wind to give the balloon a chance to go up as fast as it can before finally releasing MAGE.
Go MAGE! Go MAGE!
Finally, MAGE was on its way. It was a beautiful, beautiful launch, and it was quite obvious that it was going up a lot faster than MAGE 1. Now, the original MAGE obviously had a GPS tracker. Nay, it had two GPS trackers, one as a backup. This also gives you your altitude, but with MAGE 2 we made an improvement. We had another sensor. This sensor would record both temperature and atmospheric pressure. So we have got a wealth of telemetry data which is now displayed on the screen around the image. So let me give you a quick tour of what we've got here. At the bottom we've got two graphs. The one on the left is temperature in centigrade, the one on the right is atmospheric pressure in pascals. The entire data set is already graphed out. The current position is marked by the blue line with the red dot where it crosses the graphed data. Top left, we've got the upward facing balloon cam. Keep an eye on that, it's quite interesting. Next to that, and facing 180 degrees from the main MAGE experimental camera, we've got a wide angle camera. That's just for the view. Both the main MAGE camera and that wide angle camera will be released as full length unedited videos of the entire flight from launch to recovery at a later date. In the top right quadrant we've got a wealth of information. In the left column we firstly got the number of satellites that we're currently locked onto. Below that we've got the atmospheric pressure in pascals, and at the bottom we've got how that equates to atmospheres. It's mislabeled as percentage atmosphere, so right now it's 0.927 atmospheres or 92.7%. The right hand column starts with the current temperature in degrees centigrade. It's currently slowly dropping as we rise with height. As you can see from the bottom left graph, the temperature drops and then rises again eventually. Below the temperature we've got the current altitude in meters, and at the bottom the maximum altitude achieved so far. Obviously right now as we're rising those two figures are changing in step. When we reach burst point and start to come down again, that red figure will lock on the highest achieved altitude for MAGE. Finally, down the right hand side we've got the altitude again, this time displayed as a moving ribbon. This really helps you visualise the speed of ascent and descent later on. So now you know your way around what you can see on the screen. I'm assuming that not many of you have 3.5 hours to spare to watch the entire flight right now. So what we're going to do is we're going to jump forward and jump forward all the way up to the burst point. We'll have a look at a couple bits on the way down and the landing, and then we'll investigate what we've found. So hold on to your seats, come take a ride with me to the edge of space in MAGE 2. Oh, I know where we are. This is 5,287 metres. This is the height that the original MAGE got to. This time it's well above the cloud deck, but we've been here before. I think we should head on up. Before we do though, please note that balloon cam. You can clearly see the balloon. Look at the size of it and remember it. Okay then, onwards and upwards. Our next point of interest, 8,848 metres. This is the height of Everest, the highest point on Earth. This was also a great place for a sanity check on our barometer. We know that the atmospheric pressure at the top of Everest is approximately 33.7 kilopascals. As we passed 8,848 metres, we were approximately 32 kilopascals. So that's pretty damn close. You can see from the right hand graph the atmospheric pressure, what a beautiful curve downwards it is. I noticed that, and Q noticed it as well. He did some investigation into the actual telemetry figures we received and found that our little barometer was actually pretty darn accurate. He's done a video about it. I'll put a link across the top right now and in the description below. I suggest you check it out after this video. You may have seen the trails from a few aircraft as we've been slowly spinning around at the top of Everest. Let's go up to their height and have a look around. And here we are at around 11.5 kilometres up. That's approximately 38,000 feet. This is the height that commercial aircraft tend to cruise at. We're now down to about 21% of atmospheric pressure. We're well down that curve in the right hand graph. As for the temperature, we're about -32, -33 degrees, and we're reaching the lowest before the temperature starts climbing again. Right, it's about time we started making some height. Let's go for the first big jump. Well, here we are at 20 kilometres. That's 12.42 miles high. The temperature's rising to a nice, balmy -23.9 degrees centigrade. For those flat earthers who don't believe there's an atmospheric gradient, you've got some explaining to do. We started off just over 100,000 pascals. We're now at 5,374 pascals. It's a little lower. And that equates to just over 5% of the atmospheric pressure that you and I normally live in. The atmospheric pressure is continuing to fall, but at a slower and slower rate, like you can see in that graph. How low can you go? By reaching this height, MAGE already is a success. I'm really pleased with it. A number of people have entered the competition to guess the final height, and a number of people have already now been knocked out because we're going higher. Welcome to 25 kilometres above the Earth. That's right, 15.53 miles. I think there might be something wrong, because although it's early afternoon, the sky's looking rather black. And is it just me, or does that balloon look a little larger than it did originally? If anyone's wearing a scarf, you can probably take it off soon, because the temperature is now up to minus 16 degrees centigrade. But the atmospheric pressure is still falling. 2,300 odd pascals, down from 100,000. 2.3% of atmospheric pressure. I'm not quite sure how that can be, because I don't recall us passing through any containers. Well, if everyone's ready, let's try another big jump. 30 kilometres. 30 kilometres. 18.64 miles. I cannot believe it. According to our barometer, we are now just over 1% of atmospheric pressure. And look at that balloon. It's huge. That is so much bigger than when we started off at ground level. So as we're at this great height, and before we get a burst of our balloon, I think I ought to mention the reference frame strings for MAGE, the orangey yellow and the black line below. As I said at the beginning of the video, and as you could have seen when I showed you MAGE, those are strings. They're taut strings held in place by springs. And before anyone says that they're drawn on, you can see the light and shadow passing along them. Those are real. We're going to use those to help judge any curvature that we can see. What do you mean you want to go higher? We're already at 30 kilometres. We really could get a balloon burst at any moment without warning. Just a little jump. Look, if we're going to go for more height, we're going to go for more height. Let's do it. Now this really is incredible. 35 kilometres up. 21.74 miles. Who seriously expected we'd get MAGE up to this height? And don't forget, MAGE hasn't only got up to 35 kilometres with all the cameras and trackers and whatnot, it's also carrying cargo. It's got some cat biscuits for Arnold and a Babybel cheddar cheese for me. So at this point we are plenty high enough for the MAGE experiment to see if we can see that curve. Can you see it? I think I can. But as I said at the start of the video, we were going to stop off at several points on the way up, see the burst, have a look what happens on the way down and the landing, then we'll come back for the experiments. We're not at the maximum height yet, we're still going up. We're going to do one final jump, have a look around and watch the burst. So here we are. That really was the final jump upwards for MAGE. She is approaching her burst altitude. The atmospheric pressure is well under 1% according to the readings we're getting. And that balloon is straining at the seams. It's going to let go at any moment. When it bursts, you're going to see a thing of beauty. I will give a 10-second countdown and I will replay it at slow speed so you can really enjoy it. For now, I'll let you enjoy MAGE drifting serenely at over 38.25 kilometres, and let's see how far she can finally get before she bursts. So there we have it. The final height MAGE achieved is 38,736 metres. And I haven't forgotten the MAGE patch, the competition winner with a guess of 38,421 metres, that's only 315 metres short, is Juha Eskelinen. Well done, I'll be in touch. Now MAGE no longer has her balloon. She starts to fall to earth, quickly accelerating to around 200 miles an hour. You can get a fair idea of her acceleration by looking at the altimeter ribbon down the right hand side of the screen. She's already fallen over 2 kilometers in under a minute, and she's still accelerating. Her parachute is only 3 feet across, but at that height there's barely any atmosphere to use to slow it down, and so MAGE at first tumbles like crazy, straightening up as the atmosphere thickens. Having fallen 17 kilometres to just under 22,000, she's still going fast. As you pass 14 kilometres, MAGE is still getting thrown around, but things are a lot calmer, and she is slowing. Eventually, she'll have to slow down to a speed of about 11 miles an hour in order for her to have a safe landing. At about 10,500 metres, the batteries for the wide-angle camera finally fail. They've been running for 2 3/4 hours and been down to minus 35 degrees, so it's no surprise. Thankfully, the MAGE camera, the main one, is still running. As MAGE goes through the last few thousand metres, Q and I are waiting for her. We've tracked the area she's going to land in. We're parked up and looking out for her. Despite best efforts and scouring the skies carefully, we didn't see MAGE as she finished her journey. We were only 750 metres from her final landing point. And MAGE was finally down and safe. All that remained was for us to find her. It took about 35 minutes to find her 3/4 of a kilometre away. Not bad.
We got MAGE. We've got MAGE. Oh yeah. Looks in great condition. Fantastic. Absolutely fantastic. Well done, MAGE. Gotcha. Stay sensible.
Well, as you can see, MAGE has achieved all that I could have possibly asked for it. It was a fantastic day. Big thanks, Q. I really appreciate your help. Well, I think it's about time we had a look at what we've found out. One thing that many people will find surprising is the temperature gradient. At face value, you'd expect that the higher up you get, the colder it would get, as simple as that. But as we saw on MAGE, that's not the case. We started off about 12 degrees centigrade, and as we went up through the troposphere, the temperature dropped fairly steadily to about minus 35 degrees. This would be roughly the point where we move from the troposphere to the stratosphere. Now, the reason the troposphere is warmer at the bottom is, of course, it's heated by the Earth, which is heat reflected from the sun. As you go higher and get further away, there's less heat, which actually does leave you with an interesting problem. You've got the cooler, heavier air above the warmer air, and of course, cool air wants to sink and warm air rise, so you get a lot of mixing. That's why all our weather occurs in the troposphere. After a point, the temperature gradient flips and it slowly starts rising. This is the stratosphere. Now, most of the heat for the stratosphere comes directly from the sun, and it's warmer near the top. Now, that's warm air on top of cold air. That's more stable, so that doesn't tend to mix. As a check, I found a diagram on the internet, and you can see that as you rise with height, the temperature drops until you reach the top of the troposphere. Then after a while, the temperature starts rising again as you pass through the stratosphere. Of course, we only made it about 3/4 of the way up. So little MAGE, as far up as she went, validated known science. I think we'll chalk that up as win 1 for MAGE. Now, the next thing to look at is atmospheric pressure. Now, as we know, the atmospheric pressure is nothing more than the weight of the atmosphere above pressing down. So it makes sense that at the bottom you've got the entire atmosphere above you pressing down. As you go further and further up, there is less and less of that. So you should end up with a nice, gentle curve. And that's exactly what we found with MAGE. Now, the atmosphere is held down by gravity, and at any point along that curve, the pressure just above and just below is virtually identical to that at that point. So this is why there's no reason for the atmosphere suddenly to rush in one direction or another to try and equalise, because at any point the atmosphere surrounding it is basically at exactly the same pressure. This is a very, very smooth and fine gradient. What we don't have is a pressure of, say, 100,000 pascals next to a pressure of 50,000 pascals. Because yes, under those circumstances, it would equalise very, very quickly. So once more, MAGE has taken measurements that agree with known science. Chalk up number 2 to MAGE. But rather than just readings, I think that MAGE can do a little better than that. I think it's time we had a close look at the balloon camera. Now, at launch, it's actually really hard to make out the balloon because of the clouds above. So what we'll do is we'll jump forward till we've just come out the top of the clouds. Great stuff. So let's grab that balloon cam and freeze frame it at 1400 meters. We'll do screen grabs at a couple more heights and then just before burst point. Grab the balloon cam and freeze frame just under 20 kilometers. We do the same again, just approaching 30 kilometers. Grab the camera and then take a freeze frame. And we grab the balloon camera for one last time and freeze it just before it's about to burst. The amount of hydrogen in the weather balloon is constant throughout the flight. However, the atmospheric pressure is reducing. As that pressure reduces, there is less resistance to the pressure of the hydrogen on the inside of the balloon, which therefore expands. It keeps expanding until the balloon can no longer take it, and it bursts. So MAGE has demonstrated the temperature gradient, the pressure gradient, and now visually it has shown us the massive effect that the reducing atmospheric pressure can have as you rise in height. There's only one thing left: Earth curve. So let's start off by looking through MAGE's camera. Now, this image has not been taken at any great height, but even when we're at the peak of MAGE's journey, we're not going to easily see the curve. It's only very slight. So these reference lines serve two purposes. Firstly, there's something to compare any curve against, and secondly, they're to demonstrate that the image itself has not been manipulated. There's a simple technique to accentuate any curves to enable them to be seen more easily. That's to compress the image from left to right in its width. Now the interesting thing is only curves get accentuated. If we add a number of random straight lines on this image and then compress it, those straight lines remain straight. The angle of them changes, but they remain straight. Curves are accentuated. This technique is so effective, it actually shows us a slight problem. That bottom MAGE string is straight. The issue is the tiny amount of barrel lens distortion in a non-distorting camera. It still gives us a slight curve. But as we can see from the diagram on barrel distortion, lines below the centre line are concave. The earth shape that we're looking for is convex. So if anything, this distortion works against MAGE. It will make a curve look flatter. If the earth is flat, it will make it look convex, not concave. Let's have a look at the images. This first MAGE image is at 33,456 metres. Absolutely gorgeous. Now the horizon line is just into the top third of the image. This means that barrel distortion will actually make the earth look more curved than it really is. So it's not a fair test for flat against curved, but it's interesting to look at it. So let's compress the image and now add a horizontal, perfectly straight line so we've got something to compare against. I think that's quite obvious that there is curvature. Let's zoom in a bit. So yes, curvature can be seen, but this is in the upper third of the MAGE camera, where some barrel distortion will make curves look more pronounced. So we won't regard that one as a test. However, I would like to point out that the MAGE reference line still looks straight. Let's have a look at something across the middle of the camera. Now this drop dead gorgeous image is at 35,160 odd metres. It is stunning. There is no doubt that there is curve there. That horizon line is across the middle of the field of view. So barrel distortion up or down is not going to be taking effect. That is a smoking gun. But let's have a look at it compressed. And I'll add a horizontal yellow line again for completeness. Oh look, we done got curve. I'd say it's game over for flat earth. But I think MAGE can do just that little bit better. We've seen the image of the horizon line just into the top third of the screen, where barrel distortion would help. We've now seen a horizon across the centre of the field of view, where barrel distortion should neither help nor hinder. How about the bottom third? So any distortion is working directly against seeing a curved horizon. Let's go for it. 37,705 metres in the bottom third of the screen, with barrel distortion working against it, we can see curve. Let's compress it. There is definite curve there, and you can see it's curving the opposite way to the reference string, which is only curved because of barrel distortion. Let's add that yellow line just for completeness. And there we go. Globe Earth. Suck it up, princess. I think there's one last thing to do. Let's go back to that gorgeous image. If you recall, at the beginning of the video, I showed you that graphic that André Puelma had produced that shows the calculated curve that we should see at the height of 39 kilometres. In this image, we're just at 35, but let's see how it does if we overlay it. Not bad. Not bad at all. Well, I would say that MAGE has been a massive success. It's been a ton of work, but I've had loads and loads of support. The immense support from Q, the support of you guys with super chats, patrons, members, my 3 sponsors, and André Puelma for the graphic. I hope you're all going to join me on the live discussion stream, which is going to follow shortly. If you're watching this at a later date, I'll put a link to it up there. Until next time, stay sensible, and go MAGE!